Welcome back to the void, fellow architects. Look, today we're doing a deep dive autopsy on the Sexos Microkernel Scheduler. This explainer is all about getting our team completely aligned for the final push toward absolute hardware determinism. We've wrestled enough with the probabilistic chaos of hardware interrupts, right? So it's time we lock this system down once and for all.
We've got a pretty dark covenant of an agenda to get through today. We're going to cover the lure of the suicide move, the pure IRTQ contract, the weight-free FLCHED pipeline, our invariance of the void, the deterministic event collapse machine, and finally, the APIC-locked zero scheduler lattice. All right, part one, let's get right into the autopsy of a lethal fault we affectionately call the suicide move. You all know the visceral pain of seeing this exact log output staring back at you. We slammed our heads against this general protection fault for days. The CPU was instantly rejecting our Ring 3 handoff. Why? Because it was reading a stale TSS system descriptor, index OX30, instead of a valid user data segment. It was just a brutal, deterministic ABI mismatch, throwing up a massive brick wall before its single instruction of userland code could even execute. The root cause here was literally what we call the suicide move. In our naked assembly switch to function, we were entirely destroying our own stack pointer right before the transition. See, we used RSI as the base pointer to restore our task context struct registers. But halfway through, we restored the actual user RSI value before restoring the stack pointer RSP. We were effectively blinding the CPU, fetching absolute garbage offsets from memory, and popping that fatal 0x30 system descriptor straight into our stack frame. So how do we fix the Ring 3 drop? That brings us to part two, the pure IRA-TQ contract. To escape this layout trap, we literally had to rewrite the hardware contract for task initialization. You've got to understand exactly when to use which hardware instruction here. Sure, sysride is absolutely fantastic for fast path PDX IPC between domains that are already running. But because it relies on chaotic star MSR math, it is wildly unsafe for initial spawns. Structurally, we absolutely must rely on the Cure IRET-Q handoff model for initial process spawns. It restores explicitly from a stack frame, giving us totally deterministic control over safe P-key rotations way before we ever touch user code. By meticulously building our initial stack frame, we dodge the C layout trap entirely. We properly aligned the GDT descriptors to 0x2b for the code segment and 0x23 for the stack segment at very specific byte offsets in the task context struct. Doing this completely eradicated that GP0x30 fault. No more stale TSS pointers. The hardware finally accepts the privilege drop, and QEMU successfully drops us right into our userland entry points. Part 3. Let's walk through the proven flow of the weight-free FLSCHD pipeline. With the stack poisoning fixed, our pipeline works flawlessly. It kicks off with the hardware APTIC timer tick. That immediately triggers process events, where the bootstrap processor acts as our serialization gate. Then, FCSCH steps in and pops a task from its local per-core sharded run queue. This is huge because it totally avoids global lock contention. Next, the switch to naked assembly swaps the task context, without committing suicide this time. And finally, the IRETQ transition drops us down into Ring 3 under the precise PKRU mask of the target protection domain. For instance, safely dropping into PKey 2 specifically for our linen service. Moving on to part 4. The rules of the microkernel, or as we like to call them, the invariance of the void. Listen, FLSCHD only survives if our userland strictly obeys our unyielding mathematical constraints. These are absolute invariants. We are completely shedding all bloated POSIX and Linux assumptions. There is no standard library, no LISIC, no traditional threads. We strictly forbid any cross-protection domain pointers. Everything routes purely through PDX zero-copy capability grants. And critically, FLSCHD relies entirely on cooperative forward progress via sysyield. We explicitly reject priority inversion busy waits. If your code spins endlessly, the microkernel is just going to actively bounce your calls. Part 5 covers our massive architectural pivot, the deterministic event collapse machine. As we mapped out in the architectural pivot analysis, fixing these bugs made us realize something crucial. We aren't just building a standard microkernel anymore. We've evolved into the DECM, the deterministic event collapse machine.
We stopped treating the Bootstrap processor as a traditional scheduler. Instead, it's a serialization gate. It takes the probabilistic chaos of SMP hardware, the out-of-order execution, the incoherent caches, the random interrupts, and it collapses all of that into a strictly verified, discrete logical epoch.
By making this pivot to an epoch-consistent capability router, we didn't sacrifice a single drop of performance. Actually, we gained absolute correctness under real multiprocessor hardware. We completely eliminated hidden PKRU races. SexOS is fundamentally a causal reconciliation kernel now. Because we stripped out global scheduler locks and atomics in the hot path, our context switch overhead is essentially bounded only by the physical limits of the silicon, literally just how fast it can deliver an interrupt and flush the cache line.
Finally, part 6, the next evolution of our architecture, the APC-locked zero-scheduler lattice.
This separates what we've proven from the bleeding-edge work coming up on our roadmap. We are actively going to evolve FLSCH from a general-purpose arbiter into a pure phase clock. The goal is an APIC-locked zero-scheduler execution lattice. By utilizing TSC deadline mode, we're aiming to eliminate context switching jitter entirely. We'll fire a global broadcast so the OS runs at the literal frequency of the hardware timer, rather than dynamically calculating time slices.
So the final question for all of us systems engineers is this. Are we ready to wake all 128 cores simultaneously and execute their pinned userland actors in mathematically perfect lockstep? We've poured blood, sweat, and tears into building this foundation. Now let's go build the lattice.